exercise questions of chapter Dual Nature of Radiation and Matter. In this chapter, when you calculate the energy, you can calculate in electron volt rather than joule. Okay, now question 1. Find the maximum frequency and minimum wavelength of X-ray produced by 30 kilovolt electrons. So here energy is 30 kilovolt. Now that is 3 into 10 power 4 volt. Now if the electrons are having energy 30 kilo electron volt, then actually that is a voltage. Kilovolt means it is voltage. Corresponding energy will be 3 into 10 power 4 electron volt. Now first of all, we have to find the maximum frequency. Frequency, we can use the formula E is equal to h nu, and in this case energy will be EV will be the energy. E is electronic charge, V is 3 into 10 power 4 electron volt. Actually we have to multiply the voltage by E to convert in terms of energy. Now you can cross multiply the equation so that you will get the mu is equal to EV divided by H. Substituting the values, you will get the maximum frequency. Also, you need to calculate the wavelength. So wavelength lambda, you can calculate lambda is equal to C by nu. And frequency is maximum, wavelength will be minimum, so that you can find the value of minimum wavelength. Now next, question 2, work function is given. That is the minimum energy required to eject the electrons, and light of frequency is also given. Now calculate the maximum kinetic energy of emitted electron. We have the equation. Einstein's formula H nu is equal to the photoelectric work function phi plus Ke max. Phi plus Ke max. From there we can calculate H nu minus phi is equal to Ke max. Now the frequency is given, phi is given. You can substitute the value of Ke max. If you want to calculate Ke max in terms of electron volt, then already phi is given in electron volt. Now this h nu, when you calculate h nu, actually you get the energy in terms of joule. So to change joule in terms of electron volt, we can divide this term by E. Now h nu by E is in terms of electron volt. Phi is also in terms of electron volt, so that you will get Ke max also in terms of electron volt. Substitute the values and find, you will get the answer approximately 0.35 electron volt. Now part B, the stopping potential. We have the formula. Part B, we have the formula Ke max is equal to E V naught. Now V naught we have calculated already. Ke max is 0.35 electron volt. Therefore, V naught, what will be the value of V naught? From this equation, you can see the stopping potential V naught will be 0.35 volt. So, it is way, if you have energy in terms of electron volt, directly you can calculate the stopping potential. Then maximum speed of emitted electrons. Maximum speed you can calculate using the formula half mv max square. Half mv max square is equal to Ke max, that is EV naught. So cross multiply this equation and find the value of maximum speed. Now, next question 3. The photoelectric cutoff voltage in certain experiment is 1.5 volt. What is the maximum kinetic energy of photoelectrons emitted? We can use the same principle which you have used in part B of the previous question. So, cutoff voltage is given, V naught is given as 1.5 volt. So, maximum kinetic energy will be E max will be is equal to E V naught. Therefore, the answer will be 1.5 energy we can write in terms of electron volt. So answer is 1.5 electron volt is the answer. Then question 4. Monochromatic light of wavelength 632.8 nanometer is produced by a helium neon laser. The power emitted is 9.42 milliwatt. All units you have to convert into SI unit. Find the energy and momentum of each photon. Now, the energy of the photon. So first we see part A. Energy of the photon. We have E is equal to h nu. Again, nu is equal to c by lambda. Therefore, hc by lambda you can calculate. You will get the first answer. Then energy and momentum. Momentum of the photon you can calculate using the formula P is equal to h by lambda. P is equal to h by lambda we can use. So you will get the second answer. Now come to part B of the question. How many photons per second on the average arrive at a target irradiated by this beam? Number of photons per second you have to calculate. So here take part B. Let n be the number of photons per second. N be the number of photons per second. Then energy per second. Energy per second falling on the surface is equal to n into E, where E is the energy of one photon. N is the number of photons per second. E is the energy of each photon. Therefore, Ne will give energy per second. And you know, energy per second is power. Therefore, how can you calculate the number of photons per second? Number of photons per second, N is equal to the power divided by energy of each photon. Number of photons per second is equal to power divided by energy per photon. So power and energy per photon you have calculated in part A. Power is given in the question so that we can find the answer. Now come to part C of the question. How fast does a hydrogen atom have to travel in order to have the same momentum that of photon. So the momentum of the photon is obtained from party A, P is equal to h by lambda. Now, rather than using this h by lambda formula, we want to calculate the speed, but the question says that this hydrogen atom is also having same momentum. So you can take the value of momentum from party A and use the formula P is equal to M, P is equal to MP, and cross multiply, you will get the speed V is equal to P by M. Substitute the value of P from party A and substitute the value of mass of hydrogen atom also, so that you will get the speed of hydrogen atom. Now, question 5. The energy flux of sunlight reaching the surface of the Earth is 1.38 into 10 power 3 watts per meter square. How many photons per square meter are incident on the Earth per second? Again, you need to calculate number of photons per second. Number of photons per second formula we obtained as n is equal to P by E. Now, wavelength is given. So, energy you can calculate E is equal to hc by lambda is equal to hc by lambda. So, substitute the value of E in the first formula and find the number of photons per second. Now, next question 6. In an experiment on photoelectric effect, the slope of the cutoff voltage versus frequency of incident light is found to be 4.12 into 10 power minus 15 volt second. Calculate the value of Planck's constant. We have the equation Planck's constant h is equal to E into slope. So you will get from the graph of photoelectric effect between frequency and cutoff voltage. So h is equal to E into slope. The slope is given. Value of E you can substitute, so that you will get the value of Planck's constant. Then question 7. A 100-watt sodium lamp power is given. Radiates energy uniformly in all directions. The lamp is located at the center of a large sphere that absorbs all sodium light which is incident on it. The wavelength of the sodium light is 589 nanometer. Wavelength is given. What is the energy per photon associated with the sodium light? So energy per photon, again the same formula, E is equal to hc by lambda. Substitute the values and find energy per photon. Then what is the energy, part B, at what rate are the photons delivered to the sphere? Again, you need to calculate the number of photons per second. Rate of photons means the number of photons per second. Number of photons per second is P by E. Substitute the values and find the answer. Question 8. Threshold frequency for a certain metal is 3.3 into 10 power 14 hertz. Threshold frequency means mu naught is given. Then, if the light of frequency 8.2 into 10 power 14 hertz is incident on the metal, nu is given. The frequency of incident light. Predict the cutoff voltage for the photoelectric emission. Okay, so we need to use Einstein's formula, h nu minus h mu naught is equal to the maximum kinetic energy E V naught. Now, you are asked to calculate the value of V naught. Rearrange the equation. V naught is equal to h by E into nu minus mu naught. h by e into mu minus mu naught. Substitute the values, you will get the answer. Then question 9. The work function for a certain metal is 4.2 electron volts. Will this metal give photoelectric emission for incident radiation of 330 nanometer? So here you can follow two methods here. You can convert this wavelength into frequency. Then this 4.2 electron volt you can convert into 4.2 joules. Then find the frequency corresponding to that using the formula E is equal to h nu. Then you can verify whether the given frequency is greater than threshold frequency or less than threshold frequency. Otherwise, you can follow this method also. Okay, you can use this formula E is equal to energy corresponding to 330 nanometer. We can calculate using the formula Hc divided by lambda E. What is the reason we have taken E in denominator? Because we want to get the answer in electron volt. Now, directly you can predict if this energy, what you obtain here, is greater than 4.2 electron volts, then you will get photo emission. If it is less than 4.2 electron volts, then you will not get photo emission. Okay, so substitute the values and find this method is comfortable, I feel. So here I think you will get the value less than 4.2 electron volts, so that you will not get any photo emission. You have to calculate and verify it. Then question 10, light of frequency 7.21 into 10 power 14 hertz is incident on a metal surface. The maximum speed of electron is 6 into 10 power 5 meter per second. What are electrons? Okay. What is the threshold frequency? Einstein's formula we can use for threshold frequency. We have the formula h nu minus h nu naught is equal to speed is given, so we have no other option, half m v max square. From this formula, the value of nu naught you have to calculate. Nu naught is equal to nu minus half m v max square divided by h. Substitute the values, you will get the answer. Question 11. Light of wavelength 488 nanometer produced by a laser. Okay. This light falls on a metal surface, so cutoff voltage is 0.38 volt. Find the work function of the material. Work function, again, the same formula we can use, h nu minus h nu naught. That means work function phi is equal to the maximum kinetic energy E V naught. From there, you can calculate the value of work function phi. Phi is equal to h nu minus E V naught. If you want, you can divide the right hand side throughout by E, so that you will get the answer in electron volt. Otherwise, you get the answer in joule. Question 12. Calculate momentum and de Broglie wavelength of the electrons accelerated through a potential difference of 56 volt. So about momentum, we have a direct formula for momentum. P is equal to under root 2m ev. This formula you will get from the derivation, that de Broglie wavelength of electron. So substitute the values, you will get the value of momentum. Then And de Broglie wavelength. Voltage is given, so de Broglie wavelength is equal to 12.27 divided by root B. That means angstrom will be the de Broglie wavelength. Next, question 13. What is the momentum and speed? Momentum, speed, and de Broglie wavelength of an electron with a kinetic energy 120 electron volt. Kinetic energy is given. So again, first we can have momentum. Momentum P is equal to under root 2 me. Energy is given, but you have to take care. When you substitute in this formula, energy should be in joule. Now it is given in electron volt. Therefore, value of E will be is 120 into E. 1.6 into 10 power minus 90 joules. This value in as a unit you need to substitute here so that you will get the value of momentum. Then speed. For calculating speed, you can use the formula energy is equal to half mv square. From this formula, you will get a V is equal to under root 2e by m. M is mass of electron. Substitute the values. You will get the value of speed. Then de Broglie wavelength. So in the first part, you have calculated the momentum. Therefore, de Broglie wavelength you can calculate using the formula lambda is equal to h by p. Substitute the values. You will get a de Broglie wavelength. Then question 14. The wavelength of light from the spectral emission line of sodium is 589 nanometer. Find the kinetic energy at which an electron and a neutron would have the same de Broglie wavelength. It means de Broglie wavelength is given in the question. Then, once you have the de Broglie wavelength, then we can have the formula de Broglie wavelength lambda is equal to h by p. P is momentum is equal to h divided by, again, momentum is under root 2 me. Momentum is under root 2 me. Square the equation. Then you're asked to calculate the kinetic energy, square the equation, then you will get E is equal to h square divided by 2m lambda square is equal to, substitute the values, you will get energy. When you substitute the mass of electron, you will get energy of kinetic energy of electron. And again, you can substitute the same for neutrons. Suppose this is for electron, here mass of electron you have to substitute. For neutron, again, you have to calculate by substituting the mass of neutron. Question 15. What is the de Broglie wavelength of a bullet of mass 0.04 kilogram traveling at a speed of 1 kilometer per second? Convert the quantities into SI unit and you have the formula de Broglie wavelength lambda is equal to h divided by mt. Mass and velocity are given in the question so that de Broglie wavelength can be calculated. The same can be repeated for the part B and part C by substituting respective mass and velocities. Then question 16. An electron and a proton each have a wavelength 1 nanometer. Both are having same wavelength. Find their momentum. So momentum will be same for both of them. So that you will get for part A Momentum P is equal to H divided by lambda. Substitute the values and find the momentum. Then energy of photon. So part B, energy of photon, you can use the formula E is equal to hc by lambda. Lambda is given. So you will get the value of energy. Now come to part C, kinetic energy of electron. When you go for kinetic energy of electron, you know electron is a particle. Therefore, kinetic energy formula will be P square divided by 2m. Is the equation for kinetic energy. Momentum P you got from part A, so that you can find the value of kinetic energy. Next, question 70. For what kinetic energy of a neutron will the associated de Broglie wavelength be 1.4 into 10 power minus 10 meter? So again, you can use the formula E is equal to, we have seen the formula in one of the previous questions. Kinetic energy E is equal to h square divided by 2m lambda square. Lambda is given, mass you can substitute mass of neutrons so that you will get the value of energy. Then also find the de Broglie wavelength of neutron in thermal equilibrium matter having an average kinetic energy of 3 by 2 kT at 300 Kelvin. Okay, de Broglie wavelength you are asked to calculate. De Broglie wavelength lambda is equal to h by p. H by p is equal to h divided by under root 2m e. Under root 2m e. And here, how much is energy E? Temperature is given. So energy will be 3 by 2 kT. Value of T you have to substitute in Kelvin. So that you will get the value of energy first. Once you get the energy, then you substitute that value of E in the equation for lambda and calculate the magnitude of lambda. Next, question 80. Show that the wavelength of electromagnetic radiation is equal to the de Broglie wavelength of its quantum, that is photon. Okay. So take photon. When you take photon, you can see momentum P is equal to E by C or U by C, etc. You have studied momentum of photon, energy divided by speed, and E is equal to h nu divided by C. Again, nu by C is 1 by lambda, so you will get h by lambda, or cross multiply the equation, you will get lambda is equal to h divided by p. Now next we can try to calculate the de Broglie wavelength. Okay, you go for de Broglie wavelength, then we have the formula lambda is equal to h by mv is equal to h by t. And this lambda for a radiation, this lambda is the wavelength, actual wavelength. And here, when we calculate the wavelength of the photon, again you will get h by p. So hence we can say both of these are same. Now next question 90. What is the de Broglie wavelength of a nitrogen molecule in air at 300 K? Assume that the molecule is moving with the root mean square speed of molecules at this temperature. Atomic mass of nitrogen is given. Okay, so de Broglie wavelength we are asked to calculate again. Lambda is equal to h by p is equal to h divided by mp. Now, how can you calculate the value of v in this case? Either you can directly substitute or you can use this formula half mv square. Half mv square is equal to 3 by 2 kt. Half mv square is equal to 3 by 2 kt. From that equation, you can find the value of v. V is equal to under root 3 kt by m. That's RMS velocity under root 3 kt by m. And this value of v you substitute in this formula, then you will get the wave probability of nitrogen with 300 Kelvin by substituting mass of nitrogen there. You will get the answer.